Welcome back, everyone, to part 2 on our discussion of using logistic regression for multi-class problems. In part 2, we're focusing on training the model, specifically using a grid search to figure out the best hyperparameters, and then evaluating its performance. Let's head to the notebook and see how we do. All right, here I am at the notebook where we left off last time. We have our data set up. Now it's time to actually create a model. And what we're going to do here is use a grid search CV option on our logistic regression model, which means I will say from scikit-learn linear model import, and while we could just say logistic regression CV and use the built-in methodology, personally I like to eventually use the platform of the grid search CV option. That way it's a little more generalized. So I'm going to import logistic regression the standard way, and then in order to perform our grid search, we'll actually say from scikit-learn model selection import grid search CV. Obviously, it's up to you depending on how you like to prefer if your cross-validation is performed all in the model as kind of one simple call, or if you like keeping things a little more modular and separating out your model from the grid search process. It's really up to you. So what we're going to do here is, since we're setting up our model separate from the grid search, let's set up the base model, which means we'll go ahead and say that log model is equal to logistic regression. Now, we could just set up a basic logistic regression, but let's take a quick look at the scikit-learn documentation for logistic regression to see a couple of the options we're going to be playing around with. If we come to the logistic regression page, so scikit-learn linear model logistic regression, there's definitely some hyperparameters we want to explore further. The first thing you should know is that just like with linear regression, there's actually penalty terms we can add into the gradient descent. We can perform L1, L2, or elastic net penalties in order to try to perform some regularization on the logistic regression. So all three of those are available to us. And keep in mind, if we use elastic net, we'll have to decide on an L1 ratio, just as we had to last time. So if you scroll all the way down here, you should see that at the bottom, there's an L1 ratio, keeping in mind that it's only used if it's testing out the elastic net penalty. So we'll have to provide some values for L1 ratio as well. Now, the other thing to note here is that there's a multi-class parameter, and the three options are auto, OVR, or multinomial. And essentially, a lot of times students have the question of how are we actually performing multi-class classification with logistic regression? It looks like the sigmoid function or logistic function can only push things towards 0 or 1. Well, the way we use logistic regression for multi-class problems is essentially a one versus rest approach, or OVR. And what this does is it just separates out one class at a time from all the others, and essentially builds out your model to separate one class from all the others, then switches to the next class and separates out that class from all the others, and so on. And this is known as a one versus rest way of figuring out the multi-class problem. You should also keep in mind that when it comes to scikit-learn, not every single methodology for multi-class is going to be compatible with the different solvers. So really, there are different algorithms we can use to actually solve that optimization problem. The optimization problem is that gradient descent that's being transferred to the problem on the back end. It's really the minimization of that cost function. And you'll notice that for logistic regression, you actually have lots of options. And the scikit-learn documentation tries to guide you in the best place by telling you what solvers can and can't do. So certain solvers can't handle penalty terms, and other solvers can. And also, for some problems, like small data sets, they actually say go ahead and go with a simpler solver like liblinear, where if you have larger data sets, go for something like SAG or SAGA. So you have these different options here, and what we're going to do is we'll go ahead and choose this SAGA operator. And SAG, or SAGA, the kind of variant of it, this just stands for stochastic average gradient. And then SGA, or SAGA, or SAGA is just a variant off of this. So keep in mind, you can go ahead and check out different posts on the details behind this, but all they're doing is solving this optimization problem. Since we know that SAGA also supports elastic net, and we may be interested in checking out the elastic net penalty, we'll choose SAGA as our solver. Keep in mind, sometimes if we're choosing more complex penalty terms, the number of iterations would have to be increased in order to find that minimum. The default minimum here is 100. that is essentially the maximum number of iterations that are allows for the solver to converge. We'll go ahead and just up that so we don't get any warnings that sometimes this won't converge. So I will come back here and we'll say for the logistic regression model that our solver will be this stochastic gradient, and then we're going to say multi-class is equal to OVR, or 1 versus rest. And then I'm also going to allow it to have max iterations equal to something larger. Let's just say 5,000. That way we don't get any warnings like we saw in previous lectures where it didn't have enough iterations for the gradient descent to find the minimum. So we have the basics of the log model, but I also want to add in things to search for. So I would like to check out the penalties. So what I will do is build out my parameter grid that I'm going to pass into the grid search. And the first thing I want to check out is penalty. So I'll say penalty key, penalty here, and I'm essentially going to build this out as kind of this list of options that I eventually pass into this param grid dictionary. This is just for organization purposes. You could, if you want, just build a really large dictionary. But I'm going to check out all of these, elastic net as well. And let's make sure this is a comma, not an M. There we go. So I'll check the L12 regularization and then elastic net as well. So L1, L2, elastic net, penalty terms. Keep in mind, I should also then start setting up an L1 ratio. So let's check here. I have to set up this L1 ratio if I'm going to check out elastic net. So we'll come here, say L1 ratio, and let's just have this be something like NP linspace. And I'll say go from 0 to 1, and let's check out, I don't know, let's say 10 of them. So we're going to check out 10 of those linearly spaced. Actually, let's check 20 since really the computer is doing work and it's a simple problem. We'll check out 20 points between 0 and 1 on the L1 ratio. And the other thing, the last thing, is C value, which is that lambda term for how strong should this penalty actually be. And if you check out the algorithm documentation page for scikit-learn, it actually recommends that you set up something that's logarithmically spaced. So for C, as you explore the documentation, so if you come here, you can check out the user guide link, and it will describe the C term and how it sets it up. It actually suggests that you perform a logarithmically spacing of the C values to explore. So what we can do is come back to documentation and set that up, that instead of linspace, we use from NumPy log space. And we'll have this be 0 to, let's say, something like 10, and let's have, again, 20 spaces there. Okay, and we have to add these into our dictionary. So we have the penalty term, we have L1 ratio set up to L1 ratio, and then finally C is C. Keep in mind, these keys need to match what is expected here by logistic regression. So it should be penalty, it should be L1 underscore ratio, etc. Those strings have to match up exactly, just as we've previously discussed. So we have our parameter grid set up. Now let's create our grid model. We'll say grid model is equal to a grid search CV, pass in the base case for the log model, and then pass in param grid equal to param grid. And now we have our grid search essentially ready to go. Keep in mind, a grid search for a problem that only has 150 rows of an entire data set is kind of an overkill, but we do want to kind of get used to the process here. So we have this grid model. I will go ahead and create it. And now let's fit the grid model to our scaled X training data against our Y train label. Run that, and keep in mind, it's going to give you some warnings here that, hey, the L1 ratio is only being used when the penalty is elastic net. That makes sense because we are technically also checking L1 and L2 terms, but we keep passing these L1 ratios. So for quite a few of these, it's just going to throw up that warning that, hey, I'm not using the L1 ratio, which perfectly makes sense. Okay, so again, you can make these spaces smaller if you don't want to check this much of a parameter space. We are checking quite a bit, but that's okay. The computer's doing the work for us. I'm going to fast forward in time until this is done checking out that cross-validation set. Okay, so that just finished training for me. Now what we're going to do is actually check out our model's performance. And keep in mind, if you did exactly what I just did of these ranges of penalties, etc., you should see tons of warnings complaining about that L1 ratio, but that's okay because we were feeding it L1 or L2 penalties. I'm going to scroll back down here and let's check out our performance metrics. We'll say from sklearn.metrics import we'll go ahead and check out the accuracy score. We know that's okay because we're not dealing with an imbalanced class set. And let's also import the confusion matrix. And what we're also going to do is say classification report. So import classification report and also import the plot confusion matrix in case we want to visualize the confusion matrix. So now that we've imported those metrics, let's check out our accuracy score. To do that, we have to get our predictions. We'll say 𝒖𝒍 is equal to grid model. And in fact, before we do this, let's actually check out our grid model. So we'll say grid model, check out the best parameters. So you run that. It looks like best parameters had a C value somewhere around 11.28, and L1 ratio was 0. So basically that means it's actually just choosing the penalty of L1. So the reason it set L1 ratio to 0 here is because it never chose an elastic net model that needed an L1 ratio. It just straight up chose the L1 penalty. Okay, so essentially what we have here is an L1 penalty model with this particular C value. What we could do is go back to our grid search and start testing out different C values around this range against this penalty L1. But for that, we don't really care too much for this particular data set. So we're just going to say grid model. Actually, let's head back to 𝒖𝒍 is equal to grid model predict and predict off the scaled X test. So you run that, and if you take a look at your predictions, you'll notice that it actually predicts out strings 𝒐𝒊𝒂𝒔𝒊𝒂𝒕𝒊𝒂 Versicolor, and that's okay for our accuracy score as well. We simply say accuracy between 𝒖Test versus 𝒖Prediction, and you'll notice that we get somewhere around 97.4% accuracy, so we're doing quite well. Depending on what random train test split you did, if you differed it than ours, you could see yourself get 100% accuracy on this test set because this is an extremely small data set, and we saw that some of the classes were easily separated. In fact, if we do a confusion matrix on this, so confusion matrix of 𝒖Test versus 𝒖𝒍, you'll notice that actually this diagonal essentially indicates that everything was perfect except for 1 point in the test set. So we essentially only misclassified 1 point. And if we want, we can also plot this out with plot confusion matrix. Recall that plot confusion matrix actually takes in the model first and then the scaled data, so scaled X test, and then the test labels. So it does the 𝒖Prediction step for you. You run that, and you essentially see the exact same thing, where just one Versicolor was, or exactly one Virginica was predicted as Versicolor incorrectly. What's nice about the plotting is you can see the labels directly as strings. Okay, so finally, let's print out our classification report. We'll say print classification report on 𝒖Test and 𝒖Prediction. Check this out. And again, you'll notice that our precision, recall, and F1 score for the 𝒐𝒊𝒂 class was absolutely perfect. And that makes sense because we saw 𝒐𝒊𝒂 was easily separated from the others. Now to finish off the lecture, I do want to point out that the built-in plot ROC function in scikit-learn does not currently work automatically with multi-class situations. In fact, if you said from sklearn.metrics import plot ROC curved and try to plot the ROC curve, so it says plot ROC curve, we could have passed in that grid model, passed in the scaled X test data and 𝒖Test, it will complain that it cannot work multi-class. So it says this and says, hey, grid search CV should be a binary classifier. So the question arises, what do we actually do here? Well, luckily for us, and this is linked for you in the lecture notebook, if you go to the receiver operator characteristics section of the documentation underneath auto examples, model selection, plot _ ROC, it will show you an example of using the plot ROC function, but it also shows you how to plot ROC curves for the multi-label problem. And essentially what you have to do is just copy and paste this code, and what it does is it's going to show you how you can plot a curve for each of these. So I'm going to copy and paste this code from our notebook that already has it set up for you as a function call. So what I've gone ahead and done here is I'm going to copy and paste from the lecture notebook. There's two imports you have to do, which is ROC curve and AUC, which are essentially reporting metrics that don't actually plot anything. And then there's a function that we set up for you called plot multi-class ROC that you can actually use in order to pass in the classifier X test and Y test, number of classes, and then your figure size as well. So now that that's set up for you, you should be able to just call plot multi-class ROC, and then pass in the grid model, scaled x test, y test, and then the number of classes you expect, since it's essentially running a loop in here. So say n classes is equal to 3. Run that, and it creates the figure for you. You'll notice that for label 2, which was setosa, it's that perfect receiver operator characteristic where you get 0 false positives and you get 100% true positive rate. And then we also have here another one underneath it for, I believe it's label 0, which is also perfect. You only get this kind of squiggly ROC curve as expected for one of the classes. This is a special case because we classified everything correctly except for this one point, which was Virginica. So don't expect in real life all your receiver operator characteristic curves to look so nice. Okay, that's it, and I'll see you at the next lecture.